Let us start with Module 2. Module 2 is regarding solar thermal systems. So the outcome which is expected from this particular module is, upon completion of this course, the students will be able to explain the sun-earth angles, the various solar radiation measuring instruments and solar energy collectors, as well as to solve problems related to it. The various contents of this particular module are basics of solar energy, solar constant, sun-earth angles, the different solar radiation measuring equipments, as well as solar energy collectors. So before going into the key parts of the module, let us understand something about solar energy, some basics about solar energy. So we are familiar with solar energy. We have seen some of the factors related to it in the first module itself. So we know solar energy is the ultimate source of all other sources of energy. It is the ultimate source of every forms of energy. And it is the most important renewable energy resource. So why we are relying more on solar energy? Because solar energy is a readily available, free and non-polluting source of energy. Huge amount of energy is being liberated from the sun, and the solar energy acts as the source of every other forms of energy. So this solar energy received in the earth in the form of radiation can be utilized, can be harnessed mainly in two different ways, and based on that, the way in which solar energy is utilized, solar energy systems are of two types. They are solar thermal systems and solar electric systems. So what are solar thermal systems? So in solar thermal systems, the thermal energy or the heat energy of solar radiation is utilized. And this heat energy can then be converted to mechanical energy or electrical energy as required. Whereas in solar electric systems, the solar energy is directly converted to electrical energy by using photovoltaic panels. So solar thermal systems and solar photovoltaic systems are two different classifications of solar energy systems. So in this particular module, in module 2, we will be discussing about solar thermal systems. So we know that the energy released from the sun is very high. Tremendous amount of energy is being generated from the sun. And the energy supplied by the sun in 1 hour is very high, that it can supply all the energy needs of the human population in 1 year. So നമുക്കറിയാം സണ്ണിൽ നിന്ന് നമുക്ക് കിട്ടുന്നത് a very huge amount of energy is available from the sun, and ആ എനർജി എന്ന് പറയുന്നത് ഒരു മണിക്കൂറിൽ നമുക്ക് സണ്ണിൽ നിന്ന് കിട്ടുന്ന എനർജി എന്ന് പറഞ്ഞാൽ എൻറ്റയർ ഹ്യൂമൻ പോപ്പുലേഷൻ്റെ ഒരു വർഷത്തെ മുഴുവൻ നീഡ്സിനെയും സാറ്റിസ്ഫൈ ചെയ്യാനുള്ള എനർജി നമുക്ക് ഒരു മണിക്കൂർ സണ്ണിൽ നിന്ന് പ്രൊഡ്യൂസ് ആവുന്നുണ്ട്. So we cannot utilize all that energy, but the energy released from the sun is very high. It can supply the energy released by the sun in 1 hour, can supply all the energy needs of human population in 1 year. So but we cannot utilize all that energy. So how in this much of amount of energy is released in the sun? What is the reason for such a high energy in the sun? So we have heard about it. In sun, energy is released, thermal energy is released as a result of nuclear fusion reaction. So various thermonuclear reactions occurs in the sun, which is mainly the nuclear fusion reaction. That reaction is given here. The most important, several fusion reactions takes place in the sun, but the most identified fusion reaction in the sun is given here. That is 4 hydrogen atoms or 4 protons combines together to form helium atoms. So hydrogen atoms combines together to form helium atoms. So in this process, energy will also be liberated. Thermal energy is liberated. When 4 hydrogen atoms combines together to form helium atoms, 26.7 mega electron volt of energy is generated. So this is not a very high value. So 26.7 mega electron volt is equivalent to 4.26 into 10 raised to minus 13 joules. So that is a very small value. So but in sun, in 1 second, about 600 million tons of hydrogen atoms are being converted to helium atoms. So ഒരു ഫ്യൂഷൻ റിയാക്ഷൻ 4 ഹൈഡ്രജൻ ആറ്റംസ് ചേർന്ന് ഹീലിയം ആറ്റംസ് ഉണ്ടാകുന്ന ഈ റിയാക്ഷൻ, ആ ഒരു റിയാക്ഷൻ നടക്കുന്ന സമയത്താണ് 26.7 മെഗാ ഇലക്ട്രോൺ വോൾട്ട് റിലീസ് ആവുന്നത്. സോ ലൈക്ക് വൈസ് 600 million tons of hydrogen atoms are converted to helium atoms in 1 second in the sun. So energy liberated, total energy liberated will be a very high value. Tremendous amount of thermal energy will be released as this fusion reaction. And how energy is released in this process? So when hydrogen is being converted to helium, the mass of helium atom thus obtained will be less than that of hydrogen. So we know the conservation of mass, principle of conservation of mass. Mass can neither be created nor be destroyed. It can be changed from one form to another. So here the change in mass. So when hydrogen is converted to helium, there is a reduction in mass, and that change in mass is converted to this energy. So that is how energy is generated during nuclear fusion reaction in the sun. So now the energy is radiated by the sun in the form of electromagnetic waves. So that thermal energy in the sun is liberated or radiated to the earth, to radiated out of the sun in the form of electromagnetic waves, and 99% of that radiation have wavelengths in the range 0.2 to 4 micrometers. So if we consider the case of Earth, the solar energy reaching the top of the Earth atmosphere consists of 46% visible light, 46% infrared radiation, and remaining 8% of ultraviolet radiation. The output power of the sun is about 2.8 into 10 raised to 23 kilowatt, and the energy reaching the earth is about 1.5 into 10 raised to 18 kilowatt hour per year. So now let us see what extraterrestrial and terrestrial radiations are. So here in this diagram, the propagation of solar radiation through Earth's atmosphere is shown. So here, this is the upper limit of Earth's atmosphere. So above that, the region, that is the region outside the Earth's atmosphere, is known as extraterrestrial region. And the solar radiation falling on the extraterrestrial region is known as the extraterrestrial radiation. Okay, so solar radiation falls on the extraterrestrial radiation on top of the Earth's atmosphere, and a part of that is scattered and reflected back, and remaining radiation will enter into the Earth's atmosphere. So this is the Earth's atmosphere, and if we consider the radiation entering into the Earth's atmosphere, so this region, Earth's atmosphere, is known as terrestrial region. The solar radiation entering into the atmosphere, Earth's atmosphere, is known as terrestrial radiation. Okay, so after entering into the Earth's atmosphere, a part of the radiation will directly reach the Earth's atmosphere without being scattered or absorbed by molecules or dust particles in the atmosphere. So there will be moisture, pieces of clouds or dust particles in the atmosphere, and when radiation is passing through the atmosphere, a part of the radiation will be absorbed or scattered by these components in the atmosphere. But a part of the radiation will directly reach the Earth atmosphere, and that is known as beam radiation. The radiation that is directly reaching the Earth's atmosphere without being scattered or reflected or absorbed is known as beam radiation or direct radiation. While a part of the radiation will be scattered or absorbed or reflected back, and the radiation reaching the surface of the Earth from different directions is known as the diffused radiation. So, solar radiation, Earth's atmosphere ne പുറത്ത് fall ചെയ്യുന്ന solar radiation പറയുന്ന പേരാണ് extra-terrestrial radiation. Atmosphere ne പുറത്തുള്ള region ആണ് extra-terrestrial region. So the solar radiation falling in that region is known as extra-terrestrial radiation. Now, a part of the extra-terrestrial radiation enters the Earth's atmosphere. In Earth's atmosphere solid particles ഉണ്ടായിരിക്കും, കുറേ ഗ്യാസസ് ഉണ്ടായിരിക്കും, ഡസ്റ്റ് ഉണ്ടാവാം, മോയ്സ്ചർ ഉണ്ടാവാം. സോ അത് ഈ പാർട്ടിക്കിൾസ് കുറച്ച് എ പാർട്ട് ഓഫ് ദ റേഡിയേഷനെ അബ്സോർബ് ചെയ്യും, അല്ലെങ്കിൽ ഇത് കാരണം സ്കാറ്റർ ആവും. അങ്ങനെ ഡയറക്ഷൻ ചേഞ്ച് ചെയ്ത് വരുന്ന റേഡിയേഷൻ പറയുന്ന പേരാണ് ഡിഫ്യൂസ്ഡ് റേഡിയേഷൻ. പക്ഷേ ഈ അബ്സോർപ്ഷനോ സ്കാറ്ററിങ്ങോ ഒന്നും നടക്കാതെ ഡയറക്റ്റായിട്ട് എർത്തിൻ്റെ അറ്റ്മോസ്ഫിയറിൽ എത്തുന്ന റേഡിയേഷനെ പറയുന്ന പേരാണ് ബീം റേഡിയേഷൻ. സോ ദർ ആർ beam radiations or direct radiation and diffused radiation. So as we have said, solar radiation that has not been absorbed or scattered and reaches directly from the sun is known as direct radiation or beam radiation. So it is here beam radiation. And the solar radiation from the sun, after its direction has been changed by reflection and scattering by atmosphere, is known as the diffused radiation. So the total solar radiation received at any point on Earth's surface will be the sum of direct radiation and diffused radiation, or beam radiation plus diffused radiation. So this total solar radiation is also known as global radiation. So global radiation also means the total radiation, total amount of solar radiation received on a particular location of Earth's surface. So let us see some more definitions related to solar energy. So one is insolation. Insolation means the total solar radiation received on a horizontal surface of unit area on the ground in unit time. The radiation received on a horizontal surface of unit area on the ground in unit time. So insolation എന്ന് പറഞ്ഞാൽ നമ്മൾ ഗ്രൗണ്ടിലുള്ള എർത്തിൻ്റെ ഗ്രൗണ്ടിലുള്ള സർഫസിലുള്ള ഒരു ഹൊറിസോണ്ടൽ ഏരിയ കൺസിഡർ ചെയ്താൽ, യൂണിറ്റ് ഏരിയ, ഒരു യൂണിറ്റ് ഹൊറിസോണ്ടൽ ഏരിയ കൺസിഡർ ചെയ്താൽ ആ ഏരിയയിൽ യൂണിറ്റ് ടൈമിൽ ഫോൾ ചെയ്യുന്ന എനർജി. ഇറ്റ് മേ ബി ഇൻ 1 day or we can express the value in 1 second, 1 minute, like that. യൂണിറ്റ് ടൈമിൽ യൂണിറ്റ് ഏരിയയിൽ ഫോൾ ചെയ്യുന്ന സോളാർ റേഡിയേഷൻ, അതാണ് ഇൻസൊലേഷൻ. നൗ ഇറേഡിയൻസ്. Irradiance is a measure of power density of sunlight in watt per meter square received at a location on the Earth. So power density means power per unit area. So Earthil നമ്മളൊരു യൂണിറ്റ് ഏരിയ കൺസിഡർ ചെയ്താൽ അവിടെ എത്ര പവർ റിസീവ് ആവുന്നു, അതാണ് ഇറേഡിയൻസ്. Now irradiation. So two terms are different. Irradiance and irradiation are different. Irradiation represents the energy density. Irradiance represents the power density, whereas irradiation represents the energy density, that is energy received, how much kilowatt hour of energy is received per unit volume. So energy received per unit volume on Earth's surface, that is known as irradiation. So another important term related to solar energy is the solar constant. So what is solar constant? Let us see. Solar constant is basically the rate at which solar energy reaches the top of the Earth's atmosphere. It's known as solar constant, and it is denoted as ISC, solar constant. So it is the rate at which solar energy arrives at the top of the Earth's atmosphere. Now we can define this solar constant as the energy received from the sun per unit time on a unit area perpendicular to the sun's direction at the mean distance of the earth from the sun. So it is the energy received from the sun per unit area. That area should be perpendicular to the direction of sun's rays. Sun's direction means the direction in which sun's rays are coming. So if we consider a unit area on the earth's surface, and that area should be perpendicular to the direction of sun's rays, and it should be located at a distance which is equal to mean distance of the earth from the sun, and the energy received on that area per unit time is known as the solar constant. That means, so ഇത് എർത്തും സണ്ണും തമ്മിലുള്ള മീൻ ഡിസ്റ്റൻസ്, ആവറേജ് ഡിസ്റ്റൻസ് എന്ന് പറഞ്ഞാൽ ദിസ് മച്ച് 1.495 into 10⁻11 meters, or this distance is known as 1 astronomical unit. So സണ്ണിൽ നിന്ന് 1 astronomical unit ഡിസ്റ്റൻസിൽ എർത്തിൽ ലൊക്കേറ്റ് ചെയ്യുന്ന ഒരു യൂണിറ്റ് ഏരിയ കൺസിഡർ ചെയ്താൽ ആ ഏരിയ എങ്ങനെയായിരിക്കണം? ഇറ്റ് ഷുഡ് ബി പെർപെൻഡിക്കുലർ ടു ദി ഡയറക്ഷൻ ഓഫ് സൺസ് റേസ്. ആ പർട്ടിക്കുലർ ഏരിയയിൽ യൂണിറ്റ് ടൈമിൽ ഫോളോ ചെയ്യുന്ന സോളാർ എനർജി പറയുന്ന പേരാണ് സോളാർ കോൺസ്റ്റൻറ്റ്. So that it is the energy, solar energy received on a unit area on the earth's surface. So unit area which is perpendicular to the sun's direction and located at the mean distance from the sun and from the sun to the earth per unit time is known as the solar constant. So സണ്ണും എർത്തും തമ്മിലുള്ള മീൻ ഡിസ്റ്റൻസിൽ എർത്തിൽ ലൊക്കേറ്റ് ചെയ്തിരിക്കുന്ന ഒരു യൂണിറ്റ് ഏരിയ, എർത്തിൽ ലൊക്കേറ്റ് ചെയ്യുന്ന ആ യൂണിറ്റ് ഏരിയ, ആ ഏരിയ എങ്ങനെയായിരിക്കണം? സോളാർ റേസ്, സൺസ് റേസിൻ്റെ ഡയറക്ഷന് പെർപെൻഡിക്കുലർ ആയിട്ട് ലൊക്കേറ്റ് ചെയ്തിരിക്കുന്ന ഒരു യൂണിറ്റ് ഏരിയ. ആ യൂണിറ്റ് ഏരിയയിൽ യൂണിറ്റ് ടൈമിൽ റിസീവ് ചെയ്യുന്ന സോളാർ റേഡിയേഷൻ്റെ എമൗണ്ട്, സോളാർ റേഡിയേഷൻ എത്ര, ആ എന്ന് ഡിനോട്ട് ചെയ്യുന്ന കോൺസ്റ്റൻ്റ് ആണ് സോളാർ കോൺസ്റ്റൻറ്റ്. ആൻഡ് ദ വാല്യൂ ഓഫ് സോളാർ കോൺസ്റ്റൻറ്റ് ഇസ് എസ്റ്റിമേറ്റഡ് ആസ് 1367 watt per meter square. So this value is given by the NASA. The value of solar constant is 1367 watt per meter square. So but this value, this 1367 watt per meter square is just an average value. That means the solar constant will not remain constant. It will vary. Why? So as the sun's distance and activity varies throughout the year, the solar constant also varies. So we know that the sun's distance changes. That means we know that Earth is revolving around the sun in an elliptical path. So the distance between sun and earth will be different at different times. So due to this change in distance between the sun and the earth, and due to the change in activity of the sun throughout the year, the value of solar constant also changes. So sun and earth തമ്മിലുള്ള distance ഒക്കെ change ചെയ്യും അല്ലേ? Elliptical path, how will be an elliptical path? See, this is the sun, sorry, if this is the sun, the earth is revolving around the sun in an elliptical path like this. It is not a circular path. In an elliptical path, the earth is revolving around the sun. So this is our earth. Earth is revolving around the sun in an elliptical path. So if earth is here, the distance between sun and earth will be high, and when earth revolves around the sun and comes at this point, the distance is less. So more energy will be received at that time, like that. So solar constant varies due to variation in distance between sun and earth, as well as due to variation in the activity of sun. So solar constant is not actually a constant. The value given as 1367 watt per meter square is just an average value, and the actual value will varies by 3% in either direction. So actual value of solar radiation can be either 3% more or 3% less than this particular value. Okay. So now there is an equation for extraterrestrial radiation. We know what extraterrestrial radiation is, and the extraterrestrial radiation is expressed in terms of solar constant as IEXT, that is extraterrestrial radiation, equals to solar constant into 1 plus 0.033 into cos 360 N divided by 365 watt per meter square. So amount of extraterrestrial radiation reaching per unit area is given as ISC into 1 plus 0.033 cos 360 N divided by 365. And in this equation, this N denotes the day of the year, that is the day of the year counted from 1st January. So if we are considering a particular day, N means how much days are there from January 1st to that corresponding day. So if I am considering February 2nd, February 2nd ആണ് എടുക്കുന്നതെങ്കിൽ N corresponding to that day എത്രയായിരിക്കും? January 1st തൊട്ട് കാൽക്കുലേറ്റ് ചെയ്യണം. January 1st തൊട്ട് 31st വരെ 31 ദിവസം plus February 1st 2nd, so 33. So from January 1st to that particular day, how many days are there is denoted by this particular constant N, this variable N. So this is how solar constant can be calculated from the value of extraterrestrial radiation.